right, here we go. Learn IPv6 with IPVDRE, IPv6 address types, and how to configure IPv6 addresses on Cisco routers. So I'm going to take this opportunity to make it clear that we are going to be using the CCNA exam objectives as a loose guide, or maybe more of a stricter guide for how we're going to be talking about IPv6 in this IPv6 video series. We're also going to be configuring IPv6 addresses on Cisco routers. We're going to be using Packet Tracer. And when I get more comfortable, I'm going to be using CML. Yes, I bought CML finally because I want to dive into my CCNP studies because I'm working on networks at work. I'm getting more into the weeds, the granular stuff, getting a little bit more, I guess, more advanced with a lot of things at work. So I figured, you know what, I want to stay ahead of the curve and be prepared to lab things up that I'm curious about. And CML allows for me to do that. So if you're interested in studying for or just going down the whole Cisco track like I am, I'd highly suggest that you get CML. CML stands for Cisco Modeling Labs, and it allows for you to really dive into your studies without having to worry about the physical equipment. Even though I highly suggest that you get physical equipment, I have about 7 devices stacked on my desk behind this camera right now, and I'll be using CML with my physical equipment because apparently the nodes in CML can actually communicate to devices outside of the lab workbench, if you will, and I find that to be super cool. So I'll be using CML to dive into more of the deeper concepts, probably even use it to do some IPv6 stuff down the line as well, just to get more familiar with it, right? So now that that's out of the way, what else do I have to say? Oh, this is not a complete study guide. I wouldn't say that you can watch all of these videos and then you know everything you need to know about IPv6, whether it's for the CCNA or if you're watching because you're studying for the Network Plus and you need to get familiar with IPv6, that it'll prepare you for your Network Plus. No, I think this is more of like a review and a reinforcement, a study guide, scaffolding for your IPv6 knowledge. I'm not going to get too granular, but if you want to get granular, I highly suggest that you go over to Jeremy's IT lab on YouTube. He has a whole free complete course for the CCNA, and he gets into the nitty gritty with this stuff. But I'm still going to be using the CCNA exam objectives. We're going to be configuring IPv6 on Cisco routers, even though we can probably do it on other devices and stuff, but I only have Packet Tracer and my Cisco equipment here, right? So that's pretty much that. You know, let's continue on with the series. So this is video 2, and we are going to, as I mentioned in the beginning of this video, be going over IPv6 addresses and how to configure them on Cisco routers, right? So we're gonna be going over this stuff, right? And we're going to be covering 5 IPv6 address types, which are global unicast, unique local, link local, Anycast, and multicast. Real interesting stuff. So global unicast addresses. We had like a brief introduction to global unicast addresses in the last video of this series, right? And global unicast addresses are akin to public IPv4 addresses. These are routable IPv6 addresses where a node is assigned this address. This address is registered with IANA, ARIN, the ISP, whatever. It's a registered IPv6 address, and it's unique to that. It's globally unique to that node, right? It's similar to how in IPv4 public IPv4 addresses are unique to one or different outside interfaces on NAT devices, right? So, same thing with IPv6. These GUAs, Global Unicast Addresses, are routable on the internet and must be registered, right? They're globally unique. Once a node is assigned this address, no other node in the whole universe should have it, right? That's if we have this interconnected universe using IPv6, because I believe we have enough IPv6 addresses for the whole universe. Like, if you see that number, we went over this number in the last video, and I don't even know how to say it, but it's a really big number. And apparently it's enough for, I guess, every device on this planet to have an IPv6 address. So that's cool, right? So global unicast addresses range from 2000 :3, right? That's that whole range specified by this right here, right? So what that looks like is 2000, 2, 3, FFF, FFFFFFFFFFFF, all of the Fs, right? So that's the range. And we got to remember that global unicast addresses consist of 3 sections or 3 parts. The global routing prefix, which is typically /48s assigned to enterprises. The subnet ID, which is a /16, and the interface ID, which is /64, right? So 48 bits, 16 bits, 64 bits gives you 128 bits, right? So here's an example right here, right? We got 2001 0db8 00000000, right? That is the global routing prefix. And then we have the subnet ID. And remember, subnetting is super easy in IPv6. All we need to do is we could do something as simple as this, and then we could just increment it by 1 each time. And you'll have a crap ton of addresses. It's pretty ridiculous how easy it is, right? So this is, again, 16 bits. And then we have the 64-bit interface ID. We're going to learn something cool about how to generate unique interface IDs later on in this video, right? So the global routing prefix, the network address or the site's prefix. So it's not necessarily the network address. I was a little bit inaccurate with that. This would kind of be the network address slash network prefix, if you will, right? It's kind of similar to IPv4, where we have the subnet mask, which determines what the network ID is, or it helps us to find the network address, right? And it's typically 48/48. And again, when an enterprise needs some IP addresses, they'll typically get assigned a /48 block of addresses. They can do their own subnetting right here and, keep it moving, right? Now the subnet ID, here's the best part of IPv6. Easier subnetting via the subnet ID. If you're not a masochist and you choose a 64-bit interface ID along with the 48-bit global routing prefix, you get 16 bits for your subnet ID, right? This is a ton of subnets, right? This is great for subnetting because you'll have 16 subnet bits to work with, which amounts to 65,536 subnets. There's more than enough addresses for anything you'll ever want to do with IPv6. This is one of the reasons why I love it, because the address spaces are so large and it makes it so easy to subnet. Hopefully we don't waste these either. I don't see how we can, but hopefully we don't waste these. I'm not really a big math person. I'm good at math, really good at math, but this is a really large address space, 128 bits, and I can't see how we can screw this up, right? So subnetting is super easy with IPv6. Just increment the subnet ID to create a new subnet. That's literally it. That's what I explained earlier with this right here, right? The next subnet over would be 0002. And you can just keep on doing that. Keep on doing that. And you have so many subnets, right? So many. Okay, now, it's a little bit interesting. I like the interface ID part. So this part of the IPv6 address uniquely identifies the node on the subnet. So this is equivalent to the host part of an IPv4 address. It's advisable to use 64 bits for the interface ID in order to take advantage of Slack. I believe what I actually meant there was EUI 64, but I believe Slack also works with that. I'm not even gonna look it up because I kind of forgot. Wait, let me check real quick. I believe Slack also uses EUI 64. Forgot. Let's look. I'm looking in this IPv6 fundamentals textbook. Let me see. Yeah, I believe it does. Yep, I believe it does. Slack does use EUI 64. We're going to dive more into that later on, but Slack uses a different command. I think it's IPv6 auto config. We're going to go over that in the lab, but I believe it's IPv6 auto config, and it'll automatically configure an IP address. But what it does is it uses the prefix advertised by the router, right? So if the router advertises 2001 DB8 00000000, the router advertises this whole prefix right here, excuse me. Then what it does is it'll use EUI 64 to generate the last 64 bits, the interface ID, and it'll be good to go, right? So again, I'm trying not to get too deep into it right now because we'll end up we could talk about this forever, right? So Slack is just another version it's another way to configure an IPv6 address. There's a few different ways. We're going to see that in a second. But Slack uses EUI 64, but it also uses a series of messages that allows for the device or the node to assign its own global unicast address without the need for a DHCP server, right? Hence the stateless part of Slack, right? So there's that. So the interface ID is 64 bits, the subnet ID is 16 bits, and the global routing prefix is /48. I mean, that is the basics or most of what you should know about IPv6. And I guess the most intimidating part would be the subnetting part, which is not actually intimidating at all because, again, all you do is if you have a /48 global routing prefix, you just simply increment your subnet ID to get your subnets. Simple as that. And then you have many different ways to configure your interface IDs. So, on to the next address. Unique local address. This is not to be confused with link local. Unique local addresses are similar to private IPv4 addresses. These are non-routable addresses, meaning they cannot be routed to, on, and from the internet. This is to stay within a specific realm, right? So unique local addresses are akin to IPv4 addresses, also known as private IPv6 addresses or local IPv6 addresses. They're to be used for devices that never need access to the internet and never need to be reached from the internet. So yeah, these are probably like super private devices. I don't know of. Maybe you have some internal servers. Maybe. I don't know. Yeah, maybe you have some super secret internal servers that don't need access from the internet at all and uh, don't want to access the internet. And you can use that, right? So allows for sites to be combined or interconnected privately without having to worry about address conflicts because of such large address space. So you can again with IP, you're going to see in a second with IPv6, you have such a large address space, and then there's mechanisms in place that you can use to ensure that none of these addresses, if you're connecting the private ones or not, none of these addresses can ever or should ever conflict, right? And that's again the beauty of IPv6. There's so many different tools and mechanisms and processes with regard to IPv6 that allows for, I guess, better functionality, right? Probably why it's faster, supposedly, why the performance is better. So it allows for sites to be combined or interconnected privately without having to worry about address conflicts because such large address space. Plus, adding the use of EUI64 makes for it to be impossible to get duplicate addresses because EUI64 uses the node's MAC addresses in the creation of the interface ID. So not only that, but there's also a process called DAD, duplicate address detection, where the node can or device can sort of test to see if another device is using that same address, right? So I'm not going to go too deep into that right now. They are not routable over the internet. You can use them with an inside network. You don't need to register them, and they do not need to be globally unique, meaning you can have an IP address, an IPv6 address, like this right here, right? You can have an IPv6 address like this. So that's a bad color. And in your inside network, in a specific enterprise, and then you can have that same IP address on another node in another enterprise and it not be an issue because you don't need to register these addresses. You're not connecting the network. You're fine, right? So the next one. They're defined by the address block FC00:7, which is FC00:2 FD, FF, and all of those Fs, right? So those are the address blocks. You should know this. Definitely know this. And definitely know this, right? You should easily be able to recognize those answers like on an exam or a practice exam or something like that if they ask you some type of questions with regard to unique local addresses and global unicast addresses. You should be able to recognize what those ranges are, right? So link local unicast address, not to be confused with unique local addresses, which is I basically said it in the reverse for the last one, which is the ULAs, right? Link local unicast addresses are confined to a single link. In other words, a single subnet. So when we say link or segment or subnet, you can use those words interchangeably. They all mean the same thing. So a link local address is an address that is confined to that link, right? It cannot be routed outside of that link, and I don't believe the router doesn't attempt to do so, right? So only needs to be unique on the subnet. Does not have to be unique beyond the subnet. In other words, two different devices within the same private network with multiple subnets can have the same link local unicast address, but two devices on the same link, the same subnet, the same segment cannot have the same link local address. It's dang near impossible to anyway, right? Therefore, routers do not forward packets with a link local address beyond the subnet. Devices use a process called duplicate address detection, as I mentioned earlier, to evaluate whether the link local address is unique or not. So we'll go into the basics of DAD later, but just know that the host that wants to configure the link local address sends a message to its solicited node multicast address for its link local address and waits for a response. If it gets a response, it knows that it can't use that address. More details on this in another video. So basically, the solicited node multicast address is used to determine whether the address is being used or not. Just know that. There's a series of messages that's sent back and forth. I don't even say sent back and forth. If a response is received, then it knows that it can't use that address, right? So let's just keep it moving. I don't want to go too deep into that right now. Link local addresses are automatically created on IPv6 enabled interfaces, whether you use the IPv6 enable command or the IPv6 address command on Cisco routers with the interface ID generated with EUI64. We're going to go into that in a bit because we're going to start doing some IPv6 address configuration. So the link local unicast address is defined by the address block FE80 /10, right? So that's FE80 :2 or :2, FEBF, all of the F's, right? So IP address configuration. First of all, those are three, right? We just started with the first three: global unicast, unique local, and link local, right? Then we're gonna go into some configuration, and then we're gonna go into the other ones, right? So those are the first three. Just understand that the global unicast address, they're public addresses, similar to IPv4's public addresses. Unique local, they're private addresses. Link local, they stay confined to the link, right? So yeah, those are kind of like the IP addresses in IPv4, where the addresses are automatically generated, and those addresses are link local addresses. They're not routed beyond the subnet, right? It's just so that these devices can communicate with other devices on the subnet, right? All right, so IPv6 address configuration. So I put this note here so that just in case you feel like fooling around with this in your lab, you don't forget it and you start thinking that you've configured the IP addresses incorrectly, right? So to enable IPv6 routing, use the IPv6 unicast routing command to allow the router to route IPv6 packets. I got some typos in here. Also, if you want these little sheets that I made, let me know. I'll probably post it in the Discord, or I'll set up a little email thing where you can just download it if you want, right? It's funny because you would think that these are the notes that I would have taken while I was studying for the CCNA, but I'm actually doing it in reverse. I passed the CCNA, now I'm doing notes, which is hilarious to me. So now IPv6 addresses are straightforward, but also varied, right? So IPv6 address configurations are straightforward, but also varied. I'll configure each in Packet Tracer as a demonstration. So let's start with global unicast addresses. So global unicast addresses, you can configure them in one of three ways, right? You could do manual configuration with EUI64, and then there's also Slack, but we're not going to go into Slack right now because you have to have other things set up for that, right? And then we're going to use a series of verify commands. So let's come out of here and let's go into Packet Tracer real quick. So let's say that you want to enable IPv6 on your Cisco router, right? Come over here, move this. Right? So first thing you do, let's see what interfaces we have, because sometimes I don't know, right? I mean, obviously, if you're dealing with physical equipment, you'll be able to see on the device which interfaces you have. But since we're using in a simulator, emulator, whatever, we're just going to do this command: do show IP in brief. So we see that we're working with G00, G01, and G02. So what we can do is go into, well, first we want to enable IPv6 routing, right? IPv6 Unicast routing. Not necessary for our purposes here, but it's a good practice to engage. So now we're going to go into the G00 interface. No shut, got to bring it up. Now we want to configure a global unicast address. You remember what global unicast addresses start with, their ranges, or what have you. So with that knowledge, we're going to configure our global unicast address manually, meaning we're going to pretty much write the whole address out, similar to how we would do with IPv4, right? If we had an IPv4, we'd put IP address, and then we'd put the IP address, right? The 4 octets, right? But this is what we're gonna do. IPv6, not IPv5, we skipped that. IPv6 address. You can also do it like that. You can abbreviate it and then hit tab, right? And then we just type it out, right? DB8. This is just random, right? And then our subnet, so subnet ID, and then we can just randomly type out whatever we want for the next 64 bits. For the sake of time and convenience, I'm just gonna hit a double colon 1, which means that, let me see if I can go back over here, which means that the last bit of this address, right, is going to be all zeros except for 1, right? So 15 zeros and then 1, right? So let me pull this back up, messed up the flow. I'm being lazy, and that's what I did, right? And then you could put, you put /64, right? Got to put the mask. Now we want to verify that. How do we verify that? We verify that by do show IPv6 interface brief. Now we see our IP address, but we also see a link local address has been created. And just to skip ahead, we see that the link local address was created, and simultaneously it used, or conveniently it used, EUI64 to configure the 64-bit interface ID, right? But we're skipping ahead, and this video is probably going to be super long, but so here we go. So now we've configured the global unicast address using just the manual method, right? We just type the whole address out, and then we put the prefix, right, which is /64, which tells us the network part is these first 64 bits. Now, what if we want to use EUI64? That's pretty straightforward. All we need to do is, let's go into the next interface G01. All right, no shut, it's up, IPv6 address, 0 DB8. This is the global routing prefix, right? And then just do 222, it's a different subnet. We don't want them to overlap. And then we'll do double colon, Then we do /64, right? Because we're letting the router know that this is the prefix, right? This is the address, the subnet address, and we want it to generate the interface ID, the 64-bit interface ID, right? So, boom. Now let's check. Do show IPv6 interface, and we can do, yeah, let's do brief. Doesn't matter. Well, to switch it up, G01, right? So we see here the global unicast addresses, right? We see this was created, and we see that it was created with, again, EUI64, similar to how the link local was created, EUI64, and it explicitly says this is the subnet, because that's what I typed in. This is the subnet address that I typed in, right? And joined group addresses. This is a multicast address, right? All nodes. But we're gonna go into that a little later. This video is gonna be long, so yeah, let's get ready for it. All right, so we did manual configuration. We did the automatic EUI64 generated configuration for the interface ID, right? And that's pretty much it for global unicast address. Also, we can use Slack, right? But we might not be able to do that because I'm not even gonna go into that. But let's try. It might not be able to. We might not be able to do it. G00. Let's just try it. IPv6 address. IPv6. I think you can do address, and then auto config is going to be somewhere here. Auto config. Yep. Obtain address using auto configuration. It's probably not going to work. It did work. It did work, but what was I in? G00? Yeah, no, it didn't work because I'm not gonna go into that. Let's just skip ahead. I'm getting too excited about this stuff, right? All right, so let's exit out of here. So now let's delete this and let's create. So 2911. Let's do unique local. So unique local, they're private addresses, and we know that we can define them using this block right here, right? But we're basically going to use this address here, or a similar address, right? It's pretty much the same thing. Pretty much the same thing. So interface G00, we can just configure a whole IP address manually, right? So IPv6 address, and we'll do FD80 DB9, I don't know, something random, right? And this is the subnet, and then we can do :1/64, right? There goes our unique local address, our private address that's configured, right? Do show IPv6 brief. Do show IPv6 interface brief. And we can see here, once again, we see a link local address created, and we see the unique local address created, right? Now, what if we want to use EUI64? Can we do that? Let's try it. Interface G01, and then we'll do no shut. And then the next thing we'll do is IPv6 address, FD, I don't know, 880, just making stuff up. Different subnet, wait, nope. Oh yeah, just getting mixed up. And then //64 EUI 64, right? We're saying that this is the subnet address, and we're telling the router automatically generate the interface ID using EUI 64, right? So, boom. Do show IP hint brief. Oops, do show IPv6 hint brief, right? So now, what do we have here? We have this private address with EUI 64, and then we have the link local address as well, right? We're kind of killing two birds with one stone here. So whenever you're configuring global unicast addresses, unique local addresses, whenever you're configuring those, it simultaneously creates a link local address using EUI 64. That's what it does, right? So we probably don't even need to go over that one too much, right? We know that once we put a unique local or a global unicast, we know that it automatically takes care of link local. So also, I just wanted to say this real quick. Whenever you see me do this, do show IPv6 int brief. When we're doing show commands, we're not supposed to typically do show commands from the config mode or the sub command mode, whatever those modes are. We should ideally we can come out here and just enter show IPv6 interface brief if you want, but I'm lazy, so I typically just hit the do keyword so that I can see what I want to see, right? So I can verify the command straight from the configuration terminal. So we saw how to configure global unicast, we saw how to configure unique local, and we also saw how to simultaneously configure link local. Again, you automatically configure link local addresses when you configure a global unicast address or a link local address on the respective interfaces. Now, if you want to just configure link local addresses, all you need to do is this. Go into the interface, no shut if you want, and then type in IPv6 enable. Right, now let's verify it. Do show IPv6 int brief. Now we see only the link local address on this interface right here, interface G02. So these are the local and unique local. This is the link local and the unique local address, right? Configured explicitly, link local and unique local. And this is configured with EUI 64. And this was configured with the IPv6 enable command, which uses EUI 64 as well. EUI 64 is dope because it allows for us to use the MAC address, which is always unique. And then it ensures that it's unique by adding in some extra steps, which is inserting FFFE and then flipping the 7th bit, right? And we're gonna go over that in a second. So that's pretty much it for the lab portion. It's pretty straightforward. And these are the important commands that you should know, which is what we used. Unicast routing, enable, IPv6 address, and you configure the address explicitly if you want. And then you got the IPv6 address prefix. Then you got the prefix length and the EUI 64. And then you do the show IPv6 interface brief, show IPv6 interface if you want to see more details. Yeah, this is a long video. My bad. I'm probably going to try and cut these videos up into shorter portions in the future. Did not know it was going to be this long. I thought it was going to be shorter. So here we go. So let's just go over this one more time. With unique local addresses, you can do manual configuration with the IPv6 address command. Then you got manual configuration with EUI64. When I say manual configuration, I mean not using the IPv6 auto config command, right? And then of course, in each of these cases, you can verify by using the show commands, right? And so we see here now the unique local addresses has 4 parts to it. It has the first 8 bits, which defines the unique local address, which is this FD, right? Or FC, right? Then you got the next 40 bits, which is the global ID, not to be confused with the global routing prefix, but the global ID, which is 40 bits. Then you got the next 16 bits, which is the subnet ID. And then you got the last 64 bits, which is the interface ID. That's all you need to know for unique local addresses on a basic level. Now, the link local unicast address we went over just now, the IPv6 enable command automatically configures a link local IPv6 address. Configuring a global unicast address or a unique local unicast address automatically configures a link local address, as we saw in the lab just now, right? See, here's the proof. These are unique local. This is unique local, link local automatically generated. Unique local, link local automatically generated. And this was generated with the IPv6 enable command. If you were to do the same thing with the global unicast address configurations, it'd be the same thing, right? So here we go. Let's continue on. And you can also verify by using the show commands as we went over, right? Good to know show commands. Highly, highly recommend that you know how to configure and verify in that order, because you're going to have to do a lot of verification when you're in the field, because you're going to go into the field and you're going to have, and this is why labbing is so important. You're going to have these scenarios. And then within these scenarios, you're going to make assumptions. And in order for you to make assumptions and to test those assumptions, you're going to need to verify. There might be a little bit of configuration when you're probably untangling things, sorting things out, so to speak. But you always want to be able to verify with show commands. I would say if you're jumping into a large network or you're jumping into a pre-configured network, knowing how to do show commands or knowing your show commands is a lot. It's probably more important than knowing how to configure. So I would just knowing your show commands and also knowing or being able to prove how something works or to assume how something works is more important than config commands, because you can always look up config commands on the internet. You can also look up show commands, but to know which show commands to use to find the information that you're looking for is very important. And it's something that you build intuitively when you're labbing, especially when it's physical equipment. Get yourself some physical equipment. Knocking stuff over here. All right. So now, there's another important part that you should understand. You should understand how extended unique identifiers or modified EUI64 works. So this process uses the Ethernet MAC address of the node to generate the 64-bit interface ID. When using the EUI64 keyword on Cisco routers, the Ethernet MAC address is modified by adding FFFE to the middle of the address. Then the 7th bit is inverted. So there's a 3-step process involved. This three-step process for EUI64. Let's use this as an example. This MAC address as an example right here. First thing you want to do, or the first thing that happens, is the MAC address is split in half, right? So these first 6 and the last 6, right? And we use a little pipe symbol to split it in half. Now, what happens is FFFE is added to the middle. So it's added to the middle. Now we have 12 digits. And then we invert the 7th bit, right? So the 7th bit, like what does the 7th bit mean? So remember, these are the first 8 bits, because each digit is 4 bits in the MAC addresses, right? So this and this amount to 8 bits. Now, what you want to do next is you want to take 5 and 9 and you want to put them into binary. And 5 converted to binary is 0101, right? And that's 5 because you got 8, 4, 2, 1. 4 plus 1 is 5, right? We know addition. Good. Now we have 1001, right? That's binary for 9. You got 8, 4, 2, 1. 8 plus 1 is 9. Now, these are 8 bits. This is the first bit, second, third, fourth, fifth, sixth, 7th. You want to take that 7th bit and turn it on. You want to invert it, which means that you're going from 0 to 1. Now, for this number right here, you're going to have 1011, which is B. So remember, this is hex. Remember, MAC uses hex, and coincidentally, IPv6 also uses hex. So you have 8 plus 2 plus 1, right? So 2 plus 1 is 3, plus 8 is 11. So you got 0 through 9, right? And then 10 is A, and then 11 is B. So now you have B. You replace 9 with B, and now this is going to be your interface ID, right? No, it's it might be a lot to some people. Some people might get it immediately, but this is why I say you should watch Jeremy IT's lab, because Jeremy's IT lab, because he goes into the depths with all of the binary stuff, and you should already be practicing binary on a regular basis. But all you're basically doing right here is you're taking these first 2 numbers, converting them to binary, find the 7th bit, flip it, and then add that up for this number right here. And then you're gonna get a new number or a new bit or whatever, and then you just plug it in, and that's the interface ID. This is more so for you to be able to recognize what's going on, right? More than anything else. So that's pretty much it for the addresses themselves, the global, the unique local, and the link local, and also the EUI64. I think that's like probably, I'd say that's 75% of really trying to grasp IPv6. And if you want to go deeper into it, you should probably read the IPv6 Fundamentals book. That's as far as 75% as far as the addresses go. Because then now you can do static routing with IPv6. You can do many other things with IPv6. So there's that, right? So now, multicast addresses. So IPv6 has multicast addresses, just like IPv4. It doesn't have broadcast addresses, right? Unlike IPv4 that has broadcast addresses. IPv6 has Anycast addresses, and IPv4 doesn't have Anycast addresses, or at least I don't believe so, right? So multicast addresses, addresses that are one-to-many. The packet sent to a multicast group contains a unicast source address and multicast destination address. So it's usually one device that's communicating to a group of devices that chose to join that specific multicast group. All right. So it's defined by the range of FF00:8, which is FF00 to all Fs, right? So each group has its own obvious multicast address, right? So we have a little chart here. First group, all nodes, FF02:1. That's IPv6. The IPv4 equivalent is 224.0.0.1. All routers, FF02:2. 224.0.0.2 is the IPv4 equivalent. All OSPF routers, FF02:5. The IPv4 equivalent is 224.0.0.5. All OSPF designated routers and backup designated routers, FF02:6, 224.0.0.6. All RIP routers, FF02:9. The equivalent, IPv4 equivalent, is 224.0.0.9. All EIGRP routers, FF02:A, 224.0.0.10. Because you know A in hex is 10 in decimal, right? So that's pretty much, I would say, you need to know for the multicast addresses. And we saw in our little lab here, when we do this, right, G00, we know that there's no global unicast addresses. Obviously, these are unique local, right? Boom. Joined group addresses, FF02:1. That's all nodes because we configured a node. So it joined this multicast group. If we had configured EIGRP, OSPF, or if this was a OSPF DR BDR router, we would see FF02:5, FF02:6, FF02:2, right? So that's how that goes. Close out of this. So those are the multicast address groups, right? Now, multicast address scopes. This part is a little bit more interesting. So the multicast address scopes, the multicast addresses contain scopes. They're 4-bit scope field. These scopes define how a multicast packet, how far, got some typos, how far a multicast packet can travel. So FF02:2, for example, is a multicast address for the all routers group in the local link/subnet, on the local link/subnet, and can only traverse the local subnet. We know this because of the 4-bit scope field 2, which is this 2. I should have probably used a different example, but it's this 2. It's the fourth digit right here, right? And and that's link local, right? So we know this because of 4-bit scope field 2 in the FF02:2 address. So multicast address scopes. We're mainly concerned with 4 multicast scopes, or is it 5? 1, 2, 3, 4, 5. We're concerned with 5 multicast scopes. Excuse the typo once again. So the 4-bit scope field 1 is the interface local scope, or the node local scope, right? So we saw that right here. Well, we didn't see it here, but we're seeing the scope right here for the link. This is a link local, right? So that's the interface local scope. So if we see FF01, we know that that is not even going to leave the device, right? It's interface local. FF02, which is what we saw here, and then we saw FF02 double colon 1. That's a link local scope. That means that it only can traverse the link. It doesn't go beyond the link. Then we have FF05, which is a site local scope, which means that you have a specific site that packet can bounce around in, but it's not allowed to leave that site. So say you have a main site and you have a branch office site. Those sites might have site local packets that don't leave those sites, right? Then you have organization local scope, which is 8. So if you see FF08, don't confuse it with FE80, but FF08 is organization local scope, meaning within that organization, those packets don't leave that organization, right? And FF0E, it's a global scope. It can go beyond the organization, right? It has the furthest reach. So that's basically the scopes. You should know that. It's good to know, right? I don't know to what extent we're going to be using that. I know that in the field I see, obviously the OSPFs, the node, the route local, the routers. I mean the link local. I know I see those, but nothing too. I don't know. I don't see anything. I haven't seen. I don't think I've seen these scopes yet. But anyway. All right. So Anycast addresses. So Anycast addresses are kind of cool to me. So the Anycast addresses defines one to one of many. So Anycast addresses are addresses that can be deployed on multiple devices. So one address, multiple devices. So as you can see here, I have this old iPhone 5. I was playing around with it. And then I have the iPhone 11, right? So these two devices, and I have an iPad sitting in front of me. If I wanted to do some type of Anycast scenario, all I'd have to do is put an IP address on each. Put the same IP addresses on those devices, right? Bad example, but that'll kind of be like an Anycast scenario. Or better yet, let's use servers. Say we have multiple. Say I have a company called IPVDRE.tech, and I have servers with services running on them, right? Since I have these servers with services running on them, and I service maybe a large population over a large geographic area. I have servers all over the place, and then I have customers all over the place. If I have a customer that's, say I have 8 servers, and I have one customer, say I have customer 1 that needs some type of service off of one of my servers, maybe call it server 3, and it makes a request. It's going to reach out to the closest server, right? Which is going to be defined by some sort of metric. And maybe that might happen to be server 4 or server 5, whichever server it is. But it's requesting it from a specific IP address, the Anycast IP address. And the server that's closest to it is going to respond with the service. So as we see here, multiple routers are configured with the same IP address, which is advertised by a routing protocol. Hosts will communicate with the closest router configured with that address as defined by routing metric. So there's no special address ranges for Anycast addresses, which means you can either use a global Unicast address or a unique local address, but you have to specify that it is an Anycast address during config, right? So when you're configuring it, you do IPv6 address. I'd assume it'd be global, right? And then you put the Anycast keyword at the end of it. Simple as that. I would use global because obviously if my servers, I would want my servers reachable by people on the internet, right? If I have this service, right? So just remember, multiple devices, multiple servers, or what have you, have the same IPv6 address, and host will communicate with the closest router or server configured with that address as defined by the routing metric, right? So the last section we have here. Now you have some miscellaneous IPv6 addresses, which are outside of the 5 that we spoke about, but you have the loopback address here, which is just :1, equivalent to all zeros except for 1, right? And then you have the equivalent to IPv4 is this right here, 127.0.0.0/8 address range, right? We typically see 127.0.0.1, right? So, and it's used for testing by sending a packet to itself, right? We know about loopback addresses, not to be confused with loopback interfaces. Loopback interfaces is something totally different. Unspecified IPv6 address, right? It's just : all zeros, indicates the absence of IPv6 addresses, right? Or an IPv6 address. Used for IPv6 default routes. We're going to be doing some routing. I believe in the next video, we're going to be doing some routing with IPv6 addresses. If you already know how to do IPv4 static routing, this is going to be straightforward, right? Just a few, I think there's a few quirks to it. Equivalent to, it's popping up, equivalent to IPv4 0.0.0.0. And then you have an IPv4 embedded address. This is kind of weird to me, or interesting, if you will. It's an IPv6 address that contains an IPv4 address in the lower end, which is the last 32 bits of an IPv6 address, right? How would that look? Let me see if I could find an example. It's not letting me type. Let me see if I can find it. I love this book right here, IPv6 Fundamentals. Absolutely love it. I don't think it's gonna find it, but let's use this as an example. The lower 32 bits, right? So it'll be these last 8 bits right here, these last 8 digits right here, right? Say you have, I don't know why we do that, but yeah, I didn't find anything in this book. I don't know why we would use that. I've never seen a case used for that before, but that's essentially what an embedded address is. It'll use these last 32 bits right here, which will be an IPv4 address embedded into a IPv6 address. So that was pretty much it. That was an hour-long video. I don't know. I'm gonna have to make these videos shorter because I know some people don't like long videos, which is all good. That was a lot of talking. Hopefully I made it simple and easy to break down or easy to understand, because yeah, this can get to be a lot, but I think that IPv6 is not so bad once you get used to it. Yeah, I'll save changes. Once you get used to it, it's not so bad. Also, if you want this little slide, I'm more than willing to go through it again, proofread it again, correct the grammar and spelling mistakes that I missed, and I'll put it in my Discord or have it emailed to you. But that's pretty much it. Look out for the 3rd video. Not sure when, because I'm actually working now and it's kind of hard to juggle making videos and doing work, studying for certifications and all that stuff. But piece by piece, I will, write these up and then do the videos. And I don't know, if you like this video, just let me know. If you want more detail or more granular stuff, maybe I can get more granular with it. But I think the most important thing that you need to get down is labbing. Labbing is one of the most, I would say it's the most important thing, especially if you're doing a Cisco exam. Lab with physical equipment, use packet tracer also, but I think that, honestly, I think that you have an edge if you can get your hands on some physical equipment. You'll have an edge. When I first walked into my job doing the network admin side of my job, I felt so confident because I've used the physical switches at home, and I felt so confident consoling in, doing show commands, and that is a small part of your job. A small part of your job is going to be being comfortable with the equipment, because you're going to have a problem that you need to solve. There's going to be information that you need to garner, and you need to know how to garner that information as quickly and efficiently as you can, right? And being comfortable with the actual machinery is important. Knowing where the console cable is, knowing where the console port is, knowing if it uses a USB-C or what have you. For example, there's some equipment or some Cisco equipment that might need USB-Cs, right? I know I came across some. I've never used that. I've used my the blue cable. What's it called? The console cable, obviously. This is it right here. I use this in my lab, but there's going to be some times where you come across USB-C, and you need to be comfortable with understanding that that is the console cable. You need to know what to look for and all that stuff, right? And that's if you're allowed to console in. But that's pretty much it. Thank you for watching. If you made it this far, let me know if there's anything else that I can do to make these videos bring more value. And I will talk to you guys next time.